Yo guys, Drying here, and in the previous video we built this absolute monstrosity of a calculator. This is a 16-bit calculator, and currently it can add and subtract two numbers between 0 and 65,535. If you haven't watched the previous video yet, I strongly recommend doing that before watching this one. Anyways, today we will be taking this calculator to the next level. It's time to build two remaining math units, multiplication and division. Let's do this. And we're going to be starting with multiplication, and just like in the previous video, I will first explain how multiplying works in binary before we can talk about the equivalent in Minecraft, otherwise it's not going to make a lot of sense. So if you already understand binary multiplication, feel free to skip this chapter of the video. So in the previous video, I already explained the basic concept of binary and also how to add and subtract. And I also kind of touched on the subject of multiplication. I told you that by shifting the digits one space to the left, we can multiply by 2, which is fine. It's pretty handy to know, but you can't make a calculator out of it. What if you wanted to multiply by 3? You can shift 1.5 times, so we're gonna have to think of something else here. Let's first do an example in decimal. So let's do 5 times 15. You already know that's 75, but let's write it out. We can split this up by multiplying the first number by the second number one digit at a time. So first we do 5 times 5, which is 25. Now we do 5 times 1, which is 5, but because this 1 is in the second position, that's also where we write our answer. You might have thought that maybe it's 5 times 10, which is 50, so 0 goes here and then a 5 over here. That's also correct, but now you know why that's the case, why it's mathematically correct. Because if you remember, the decimal number system is a position system, just like binary. The position of a digit gives that digit a certain value. And because of that, stuff like this is possible. And now we can just add these numbers together. So 5 plus 0 equals 5 and 2 plus 5 equals 7. Our answer is 75. 5 times 15 is indeed 75. Now let's take this to binary, and because binary is also a position system, we can just do the exact same process. Let's do a small example. Let's do 3 times 5, which is 15. 3 in binary is 2 and 1, so it's 1, 1. There we go. And then 5 is 4 and 1, so it's 101. There we go. And then I can just fill this up with as many zeros as I want. It doesn't really matter. All right, so these are our numbers. We got 3 times 5. So let's do the first number times the first digit of the second number. So we have 1, 1 times 1, which is just 1, 1. And I'm just once again gonna fill it up with some zeros. There we go, that's 1, 1. And now we do the first number, which is also 1, 1, times the second digit in our second number, which is a 0. So our answer is just 0. So I don't really need to write this down here. So let's move on to the last digit, which is this one over here. So let's do 1, 1 times 1, which is also 1, 1. But this time we need to write it from here, from this position, from the third position. It's the same thing we did over here with our 5, and then we can just fill this up with zeros. So we got 1, 1, 0, 0. There we go, and now we can just add these two numbers together. So 1 plus 0 equals 1. Over here we got 1 plus 0, which is 1. 1 plus 0 equals 1. And 1 plus 0, you're not gonna believe this, it's a 2, no, it's a 1. And now we got our final answer down here, which is 1, 1, 1, 1. So that's 8 plus 14 plus 2 plus 1 is 15. 3 times 5 equals 15. It's correct. In the previous video, we built an adder or a CCA, which is this module right here, which we used for addition. For subtraction, we used the 2's complement to turn our subtraction into an addition, so I could just use the same CCA design we already had. Now here with multiplication, we found a way to also turn this into an addition. But that doesn't mean this is gonna be easy. This was the first design I was considering. It's a multiplier made by Wings, and you can see that there's actually a CCA here in the middle. So what this thing does is it works on a clock. which is this thing down here. And every clock cycle it checks the second input number if a digit is either a 1 or a 0. If it's a 0 it does nothing, it just shifts to get ready for the next cycle. But if it's a 1 it takes that first input number and puts it into this adder. And in the next clock cycle it shifts the signal 1 digit and it once again checks if the next digit is a 1 or a 0, and if it's a 1 it adds it together with the previous number, and it continues doing that for 8 cycles until we have our answer right here. And it's pretty cool, very smart to use the same CCA for everything. It saves a lot of space, but I just couldn't get it to work on the Bedrock edition. First of all, he had some monostable circuits, and can I just complain for a second here? This right here is a monostable circuit. You can see that the lamp only turns on for 1 tick, but as soon as I put 1 repeater in between, now it doesn't work. It does on the Java edition, but why does this change so much? Like, why? And there were so many other things, like, for example, in the Java edition, you can make a sticky piston, leave its block behind with a short pulse. Basically, it's like a T flip-flop. But here on Bedrock edition, that doesn't work, so I had to do another T flip-flop in between here, but this created extra delay and it messed everything up. And also locked repeaters need to be on 2 ticks on the Bedrock edition of Minecraft, which also messes everything up, because remember, it works on a clock, and this clock uses monostable circuits that also don't work. And I'm pretty sure expanding this to 16-bit would have been impossible too. Like, this is only 8-bit, it's only 8-bit and I already couldn't get it to work, so yeah. And that's when I came across a design by Benny's Cube, and this thing is compact. Like, just this part of the build, that's a CCA. It's the exact same thing as this ginormous module right here. Like, in comparison to that, this thing is tiny, which is also the downside of this design. This is a 4-bit multiplier, and it's so fast, so compact, so optimized that it's basically impossible to expand it to 16-bit, as any delay will mess it up. And also, if this thing looks a little bit weird, yeah, I had a bit of an accident with with the clone command. I accidentally cloned this thing 1 block lower inside of itself. So, yeah. This thing doesn't work anymore. And then Noobby hit me up and he was like, hey, I can show you a simple design that will work for you. And he took a few hours of his time to explain me the concept behind multiplication, and he basically explained the connection I had yet to make with multiplication and these modules in Minecraft. That's when I finally understood how these worked, and I also understood that I don't necessarily only need 1 CCA that it cycles through. So we'll take a step back here, we'll leave these complex synchronized modules behind, and if you just take a clear look at what they are actually doing, we get this. Remember the shifting we did over there, you know, with the 5? Well, we can actually do that directly with the inputs. So if we put in our first number, and with every input we shift the number 1 digit to the left, and we use the bits from the second input number to either let the signal go through if it's a 1 and block it if it's a 0. And with this we've actually completed the first stage of multiplication. And after that, all that's left to do is to add up these numbers, and that's what these orange boxes are for. Every orange box represents 1 CCA. And the reason we have so many of these is because our CCA can only add up 2 numbers at a time. And by the way, these 2 schematics are practically the same. This one is just a little bit more compact. So the first number gets inputted into all of these inputs, but right here it has not been shifted, and in the one next to that it has been shifted once. Next it's been shifted twice, 5 times, all the way up until 15 times. And with the second input number we either let the first number pass or get blocked. That's what these red blocks are for. They represent comparators which we can use to block our signals. And then all of these signals that have been either blocked or not blocked will get added together, and down here we will get our final answer. I really hope that made some sense. It's difficult to explain this, but I'm trying my best. And once again, a huge thank you to Noobby for helping me with this. So now it's time to transform this schematic into a real build in Minecraft, and I've already done a few things to prepare. You might have already spotted it, but I've been preparing the inputs for the first row of these CCAs. So 1 CCA can connect to these inputs right here, and another one can go right next to it over here. And you can see the redstone signal going up here. That's what I meant with the shifting. So let's take this signal right here, for example. Right now it's right here, but in the next row of inputs it has been shifted 1 up, and then it travels to the next CCA where it went up again, and it just keeps doing that all the way until it has shifted 16 times. So we shift every bit to the left by 1 for every input. And building this is an absolute pain. For example, right here we have a 16-bit CCA, which is basically 2 8-bit CCAs connected. But you see this gap here? Yeah, that's the problem. That gap is the reason I can't just copy paste this. I have to do everything by hand. And I'm not even close to done. So far, these are 4 inputs. I have another 12 to go. Now you might have spotted an issue here. If we're using 16-bit CCAs and also 16-bit inputs, and the input gets constantly shifted up by 1, well, we're gonna run out of space. So that's why I'm gonna have to expand the 16-bit CCA all the way up to 32-bit. Because that's also what our answer is going to be. Because if we multiply 2 16-bit numbers together, we get a 32-bit answer. And I've already built one of these right here. I don't know if you can spot it. It's like slightly bigger than the other modules in this calculator. Now don't be ashamed if you can't spot it, but it's this one right here. No, just kidding. It's this monstrosity. Yeah, this thing is absolutely massive. Like, just take a look at this, right? So this is my calculator and it's floating, like it's not touching the ground. And it goes all the way up until somewhere around this height. This thing is standing on the ground, and it's even taller. And we're gonna need 15 of these, but yeah, first I'm gonna prepare the rest of the inputs over there, and then we will have fun with these. Oh my goodness. This thing is absolutely huge. And this is just to line up the inputs. So if you come around the back here, you can kind of see that the signal gradually goes up throughout these different inputs. So I've actually kind of switched it around. Normally you use the second number to either block or not block the signals, but I'm gonna be doing that with my first number. That way everything has already been blocked, what needs to be blocked, by the time I go to my second number. And the second number, this feeds into all of these inputs over here, so you can see it crosses the first line of inputs, and this comparator logic right here, this is just to make it block when we're not multiplying. So when we select multiplying, that's when the signal can finally go through. And then yeah, the signal will travel up, and every input, every line of input, so this right here is one line, this another line, we have 16 of these lines, so this right here is our 16-bit input, it hasn't been shifted yet. And then in the next line of inputs, that's where it has been shifted by 1, and it just continues doing that. And then of course with the first number we do the blocking. So for example, let's take the second bit line right here. This just leads into another slab tower that blocks all of these comparators. This is to block the signal from going into the adder. So this happens first, and then the signal is let through into the system. So first everything gets blocked that needs to be blocked, and then when you press calculate and you have put in the second number, that's when the signal can finally go into the system and into all of these CCAs to get our result. So I guess it's now time to start pasting in all of these CCAs. Alrighty, I've removed all of the redstone lamps, which was just for testing, and now it looks even messier. But we should be ready to start pasting in our first CCA. I am so nervous, like I really hope I didn't mess up any of the dimensions here. So just to be clear, this is what we're doing right now. We're pasting in all of these CCAs. We've prepared the inputs, that's what these things were for. And now it's time to paste in all of these CCAs and connect them until we have one final output. And the one we're going to be pasting in right now is this one over here. So every one of these orange rectangles is one of these modules. This is a 32-bit CCA. Alright, so these are the row of inputs for the first CCA. Let's go down here and hopefully everything will line up. Oh. Okay, that's good. That's good. Everything is looking good. Nothing is interfering with the other redstone. This also lines up, which is perfect. I think we did it. Now it does stick out a lot. How does it look from down here? You can't kind of see it. Oh yeah, that's definitely bigger than everything else. So yeah, that's 1 out of 15. We need to paste in 15 more, and then I'm gonna have to connect all of these outputs here with the other CCAs. And I think we will do that in a small time lapse. Now this looks absolutely insane. Like, I thought these modules were big. These are for addition and subtraction. These look so small in comparison. I can kind of see now why people only used one CCA that they cycle through, because yeah, this takes up a lot of space. And this was a nightmare. I had to like go like that and then go up, break it again, and just do this. I think I did this for like 3 hours straight. And these modules right here also had to be hooked up. We have these first modules right here. 2 of these come together into a third module. And then that one comes together with another branch right here into a 4th module. And then it connects with the other half of the entire thing into one final module. And then all of these outputs get sent to the display. But I thought this was gonna be easy. Like, if you take a look at the schematic I made over there, that was simple. But no, first you have to line up all of these inputs, do the comparator logic with all of these slab towers, and then you can paste in all of these modules, but then you have to connect them. Each one of these modules has 32 outputs, which needs to go into 32 inputs of another module. And we have 15 of these modules. This was a lot of work, but it works, I think. I haven't tested it yet. So I guess let's do that right now. And if you remember Noobby, he was the one who explained me all of the multiplication and all of the schematics, and he helped me a lot. And that's why I gave him the honor to choose our first 2 numbers for a real test. And these were the numbers he gave me: 5,121 and 48,742. So let's work our way up to multiplication. Let's first do addition, then subtraction, and then we'll do the multiplication. And this is the answer it gave me for addition: 53,863, which is correct. So now let's do subtraction. So if you select this, the signal for the answer for addition will get cut off, so we don't need to worry about resetting it. Alright, for subtraction, this is the number it gave me, which is also correct. And now it is finally time to test the multiplication. There we go, our cross is on the screen right there. This number should now go away. And hopefully after some time, the correct answer will show up on screen. Ooh, it's laggy. Yeah, it's definitely laggy. Oh, that's a big number. Oh my goodness, that's a huge number. Alright, let me check that one real quick. So 5,121 times 48,742 equals 249,607,782, which means this works. Oh my goodness, this monstrosity works. Oh, I'm so happy. It actually works. That is absolutely beautiful. So of course I will be testing multiplication some more off camera to catch the ones that don't work and then bug fix it. But right now we have 3 working math units, which is amazing. And now that we've completed multiplication, I also want to update this map to see what this looks like from the air, because this is gonna look small in comparison to what the multiplier is probably gonna fill here. So I'll try to position myself in the middle, and let's update it in 3, 2, 1, and there we go. I expected there to be a little bit more down here, but yeah, still, this is huge. Now you can actually see the shape of the Wallace tree multiplier, which is that schematic I drew over there. This looks so small on a map. But then if you see it in person, it's huge. I guess when you're looking from the top down, it doesn't, yeah, you don't really see any of the blocks that are below it. But yeah, still, this is a huge math unit. Again, pretty smart decision to use the same CCA and cycle through it instead of building it like this. There is definitely a small difference in size. I mean, if you compare this to this or this, yeah, it's a little bit bigger. You might not even notice it actually, but Yeah, this is just insane. Now it is time to start thinking about division. So like I said, division is a little bit more complicated than the other ones, but I'll try my best to explain. And like we've always done, let's start with an example. Let's do 28 divided by 3, which should give us 9 with a remainder of 1, because 3 times 9 equals 27, and 28 is 1 more than 27. So I've written down 28 and 3 in binary. 28 is 11100, and 3 is 11. Now we're going to be looking at this number right here, and we're going to be checking bit by bit if this number is greater or equal to the left number. So we'll start with the first bit, and 1 is not greater or equal to 3, so we write a 0 right here. Now we're going to be looking at the second bit as well, so now we have 1, 1, which is equal to this left number over here. So first we're going to put a 1 up here, so every time this number right here is greater or equal to the left number, that's when we put in a 1, and otherwise it's just a 0. Next we grab this number and move it down here, and now we're going to be subtracting these two numbers. Now in this case they are equal, meaning that 3 minus 3 equals 0. But this isn't always the case. Sometimes you can have a 1 here. We'll see that later. So now we're going to be continuing with this bit instead of the ones up here. So we already used these two bits, so let's now bring down this 1 over here. Now we're going to be checking 1 is not greater or equal to 3, so we write a 0 up here. Next we're going to bring in another bit, so we bring down this 0 right here. Now we have 1 0, which is 2, which is not greater or equal to 3, so we once again write a 0 up here. Now we're going to take down the last bit, which is also a 0, but now the number we have right here is 100, which is 4, which is indeed greater than 3. So we write down a 1 up here, and now we can once again take this number and move it down here. So we're going to write down 1, 1, and then we can just fill up the rest with zeros. And now we're going to once again subtract these two numbers, and this time it's not as straightforward. Like over here we had 3 minus 3, which is of course just 0. But right here, it's a little bit more complicated, because how are you going to do -1? We can quickly use the same trick we used over at our subtractor over there to turn this subtraction into an addition. So we invert all of these bits, which makes it 1100, and then we add 1, so this bottom number is now 1101. I already explained 2's complement in the previous video, so I'm not going into that again. Now we can add these two numbers together. So 0 plus 1 equals 1. 0 plus 0 equals 0. 1 plus 1 equals 0 with a carry. And lastly, we have 0 plus 1, which is 1, plus 1 equals 0 with a carry. But we don't care about that carry. We can throw that away. This is all we need. This is our answer. Well, part of the answer. What we have up here is our answer, and this down here is our remainder. So let's check if this is correct. So we did 28 divided by 3, which should give us a result of 9 with a remainder of 1. This up here, 1001, is 9 in binary, so this is correct. And down here we have a 1, which is our remainder. So this is how we do it on paper. Let's now take this concept and change it to something we can do in Minecraft. So here's another schematic. This is a 5-bit divider. We get the first input number here in red, and then the second input number down here in blue. Let's now do the same thing we did over there. Let's do 28 divided by 3. So 28 is 11100, and 3 is 11. So what we were doing over here is subtracting this first number by the second number, and we do that bit by bit. So in other words, we're shifting this first number into a subtraction with the second number. So let's say the orange box right here, this is our conditional subtractor. It's conditional because it will only give an output when the answer is positive. Because if you remember over here when we did 1 minus 3, well, that's a negative number, so the output is a 0, and then we just shift and do it again. This time we had 3 minus 3, the output is a 0, which is positive. So only when the output is positive, that's when the conditional subtractor will give you an answer. Alright, let's now do the same calculation with this schematic. So first, we shift the first input number by 1, so this conditional subtractor will now get inputted a 1 right here. And now it's going to subtract whatever we're inputting here, which is 0, 0, 0, 0, 1, so it's just 1 with the second input number. So 1 minus 3 is a negative number, so the output is 0, and that is part of our answer. So now we just continue, so we shift once again. Now the conditional subtractor has an input of 3. 3 minus 3 equals 0, which is positive. So the sign bit is turned on, and this is part of our answer. And now what it does, it replaces these bits with the answer of the subtraction, which was 0, so we just turn these off. Alright, so now we continue, we just shift this bit over here. Now we have an input of 1, which is not greater or equal to 3, or in other words, 1 minus 3 is a negative number. So the sign bit is turned off, and part of our answer is a 0. Now we shift it once again, now we have 2 minus 3, which is still a negative number. The sign bit is turned off, which is also part of our answer. And now we shift it for the last time, because this is a 5-bit divider, meaning that we only have to shift a total of 5 times. So this is the last time we've shifted. Now we have an input of 4 minus 3 equals 1, which is positive. So the sign bit is turned on, this bit of our answer is turned on, and then well, it's not really necessary, but now we can change these bits down here to the answer of the subtraction. So that was just 1. And now we're basically done. We got our answer over here. Our answer is 1001, which is 9. And down here we got our remainder, which is 1. 28 divided by 3 equals 9, with a remainder of 1, which is the same we got over there. Now, of course, we're gonna have to expand this a little bit. Like, this is technically a 5-bit divider. I want to build a 32-bit divider for my 16-bit calculator, but more on that later. First, I just wanted to show you what a schematic for a 32-bit divider looks like. And yeah, that's big. That's really big. So I hope that explanation was at least a little bit clear. If it isn't, I'll give you a link in the description to one of Matt's videos where he explains all of this as well. Now let's take what we've learned and build something that isn't just a schematic on the floor. And I think I'm gonna start with the conditional subtractor. I think that's gonna be the easiest part to do. And here it is. This is a 32-bit conditional subtractor. And again, I'll explain why it's 32-bit for a 16-bit calculator in a minute. So as its core, this thing has a 32-bit CCA, which is an adder. But Ryan, you might ask, isn't it supposed to be a subtractor? Well, yeah, of course. That's why this input right here has all of these redstone blocks and torches. That's because all of the inputs are getting inverted, and then down here we have the carry in turned on as well. So we're using 2's complement once again. So how do we control the whole greater or equal to x thing? Well, we're gonna take a look at the most significant bit, which in this case is the carry out. If it's turned on, meaning the answer of the subtraction is positive, then we want the output from here. We want the answer, but if it's turned off, if the answer is negative, then we want to ignore the answer and just use the same bits again. And that's what these comparators are for. When the sign bit is turned on, then it will unlock these comparators and block these. And when it's turned off, it will block the answers and unlock these comparators, so the same input signal is getting used. So this carry just goes all the way down, and on the way down, it locks and unlocks all of these repeaters here that are connected to all of these comparators. And after that, the bits need to shift, and that's what this tower right here is for. So it takes the answer, or just the same input bits from this input bit over here, and then it travels up to the next bit. They redirect whatever signals we have unlocked to the next inputs 1 bit up. And these repeaters are locked, so we can control when we want this thing to calculate to make sure it's not getting desynchronized. So for example, it has done calculating, and now some of these lines are getting power, but it's not getting into the CCA yet because of these locked repeaters. And with the press of this button, we can unlock all of the locked repeaters in this entire CCA at the exact same time. So the only thing left to do is for the second input number, which is this one over here, to get gradually shifted in bit by bit. And we also need something to take the state of this carry out and store it somewhere to form the answer. And if you throw all of that together, you get something like this. This was an absolute nightmare to build. So this is once again a design by Matt. He made a 16-bit divider and I expanded to 32-bit, but it was not easy. I basically had to redo all of the timings and the clock. It took me almost over 10 hours to get it right. So yeah, I'm gonna try to explain what's going on here. So you see this tower right here, this is our clock. So the signal will come up here and then travel down, activating both of these glass towers. And this right one, this is where the first input number gets inputted. So when a bit is a 1, you can see that the repeater can now give a signal through that block and it will reach into this glass tower. And it will travel all the way down until it goes in here in the very first bit of this CCA. This is what makes sure that the bits gradually get shifted into the machine. And then the left tower over here, you can see that there are no pistons right here. This gets activated every time, every cycle. This is what's responsible for unlocking these locked repeaters right here for a split second, enough to let the signal pass through and lock it again, and also to save the state of this carry into this locked repeater tower over here. Sounds very simple, but everything has to happen at the perfect moment. So every cycle is 23 ticks or 2.3 seconds, and we have 32 bits, so unfortunately this one does take some time. So let's do the same calculation we did over there. So let's do 23, so 11100 divided by 3, which is 11. And when we press this button, the signal will travel all the way up and travel down and start calculating. So right now it's up there and we're gonna have to wait for it to reach these bits. That's gonna take some time. Now I could potentially make this a smarter system so it always starts calculating at the highest bit. So if you're using small numbers, it will definitely save some time. But I'm too lazy. Okay, fine, I did it. Are you happy now, internet? Well, I'm happy because we now have a faster division unit. So, yeah, I'm not gonna go into how this spaghetti monster works because it's a total mess. All you need to know is that every 4 bits it checks if there's an input and it checks if it's the top input bit. It closes access to the other input bits from the calculate spiral and it allows the signal to travel into the clock at the top bit of the input number. I just totally read that off of my script. So now let's do the same thing again. We were doing 28 divided by 3. So 1, 2, 4, 8, 16, and 4. I think that's 28. And then we got 3 over here. So this bit right here is part of these 4 bits, meaning that the signal will go into the spiral over here. Because you can see that this piston has been retracted, meaning the signal can travel into this block, into the spiral. So now if we press calculate, this should give us the answer a bit faster. And you're gonna be seeing a bunch of things in chat. That's how I debugged this. That's how I figured out the correct delays and timings. And that's also what these command blocks are for. They're not part of the design. Don't worry about that. These were just for debugging. So before pasting this into our actual calculator, I will of course remove these. I think we got some over there. We got these command blocks over here. There's one right here as well, but I still need to remove them. So let's press the calculate button. Let's fly over here and see this thing in action. So you're gonna see a bunch of lamps lighting up. You're gonna see the CCA doing its work. Not yet. Is it still? Oh, okay, there we go. So you can see the inputs getting shifted in as well on the left. And that's where our answer is slowly gonna be popping up over time. It should be done any moment now. Yeah, I think it's done. So this right here is our answer. So again, this is binary, so the value of these lamps goes from 1, 2, 4, 8, 16, 32, etc. So that means that we got the lamp with value 1 and 8 turned on. So the answer is 9. 28 divided by 3 equals 9. So this thing works. Almost. You might be wondering, what are we gonna do with the remainder? There's supposed to be a remainder of 1 in there, and I guess you could see this right here. That's a 1, but this is no accurate representation of the remainder. This is just by chance that that lamp is turned on. So right now our output is a whole number. how do we turn that into a decimal number? Well, let me tell you my secret trick that isn't very secret at all and I didn't come up with myself at all. It's finally time to talk about why in the world I built a 32-bit divider for a 16-bit calculator. You see, calculators are actually lying. The radix point or the decimal point, it's a complete scam. Let's say you're doing 1 divided by 8, your calculator will give you this, 0.128. Wait, did I just... Oh my goodness, I'm so dumb. Let's just pretend no one saw that. So let's say you're doing 1 divided by 8, your calculator will give you this, 0.125. And you might think your calculator is so smart it can work with decimal numbers. Well, you're wrong. You see, what it's actually doing is multiplying the first input number to a factor that will decide how many digits after the decimal point you want to show. So in this case, your calculator would multiply your first number, which is R1, by 1000, so it has 3 digits after the decimal point. So now it's doing 1000 divided by 8, which is 128. And then it just adds the dot in the correct position on screen for us to be able to read it. So what about the one I'm building right now? Well, I have chosen for an accuracy of 4 digits after the decimal point, which means the first input number will get multiplied by 10,000. So if we want to do 123 divided by 56, it would multiply the top number 123 by 10,000. So it's turned into 1,230,000 divided by 56. And then it would give us this number, and then the calculator would just add a dot right here. And this is the answer we will get, which is correct. And this is exactly the reason why we're building a 32-bit divider. It's because let's say we take the highest possible input number for 16-bit, which is 65,535, and if we need to multiply that by 10,000, well, now we get 655,350,000, which is way more than 16-bit. That's why I made it 32-bit, as the highest 32-bit number is over 4 billion. So now it can handle those large numbers. And that's what this thing right here does. This is what multiplies the input number by 10,000. It's basically like a smaller version of the multiplier we made in the calculator. It again uses a few CCAs and shifting of the inputs, just like we did over there. The reason why this one seems so small in comparison is because the number will always get multiplied by 10,000. So we don't need to account for all possible numbers, we just need the bits that make the number 10,000 in binary. So let's now try our example once again, 28 divided by 3, now using this module. So this right here is the first input number, it's 28, and it gives us this in the output. So this should be 28 times 10,000, so 280,000. Now we just need to copy this number over here to the input of our divider. In our calculator, this is just going to be linked up with redstone. But for now, I'm just going to do it with the levers. The second input number doesn't change though, that just stays the same. But this input number, this first one, needs to be multiplied by 10,000. And I think I've correctly copied the lamps. So let's now press calculate and see what answer it gives us. Oh, never mind, I forgot to press the reset button. Yes, I totally forgot to reset it before pressing that calculate button, but I did it again, and this time we have a way bigger number as our output. This is 93,333. And if you would add the decimal point, we would have 9.3333. So this way the answer has 4 digits after the decimal point. Now unfortunately there's one small downside, the divider doesn't round up the last digit. So if the answer is actually 0.00009 with 4 digits, it will just show a 0. But who cares about that, it's 99.9% accurate. Sometimes the last digit can be off by 1, but for me that's good enough. So now that we finally have a working divider, we can copy this build and paste it into our calculator. Alright, I think I'm ready to start pasting these things in. So on the top screen you will be able to see my perspective, and then on the bottom part of the screen you can see my camera account. So if I did everything correctly, we should now be able to paste in the first part. Oh, alright, let's try this again. Hopefully this now works. It did. And everything has been connected correctly. This is good. This is very good. So now we're going to be standing right on top of this block and then move to the left. And hopefully, if we now paste in the second part, everything should be fine. It's looking good. I think we're good here. I think it worked. So let's do this. This is the last part of the module that multiplies the first number by 10,000. All right. Okay, everything's looking pretty good. I think we did it. I think this has successfully copy-pasted the entire thing without anything going wrong. Now for the actual division module, this should be the right position to paste this. Let's see if I was correct. Okay, wait. Oh, I forgot about something. No. These lines right here, these need to connect with these lamps. And 2 blocks isn't enough for that, so I'm gonna have to... this is a pain. Okay, let's just hope this doesn't remove anything that we need. Is this still fine? Looks like it's still fine. Okay, now unfortunately the game is very laggy, as you can see. So yeah, I'm gonna have to wait a bit for the game to catch up and then I can remove the second part. Alright, after 5 minutes the game has finally caught up, so now you can actually hear the sounds the blocks are making when you break them. And also entities now work, so it's time to remove the second part of this. Okay, and now we wait again because... Yep, the game is behind again. Wait, I just noticed something. On my screen I broke the command block, but on the camera account screen it's still there. The game has like almost stopped working, like I can't pick up entities, I can't open my inventory. Also the chunks aren't loading. Like look at this. These are the chunk borders. Oh, I think the game has caught up again. Either that or it's because I've unloaded these chunks. Okay, the blocks have reappeared, which means... No. It still hasn't caught up again. Do you see that? Did you see that crouching? That was the game getting caught up with my movements. Whenever I'm flying around and I want to go down, I crouch. And that was the game still getting caught up with these. I still can't pick up entities. Oh. It's gone, and it's back. And it's gone again. What? And it's back. Okay. Oh, it's in my hand. And something else dropped here, which is a torch. Come on game, please, just let me play Minecraft. Why is deleting redstone so laggy? Okay, finally. Okay. Okay, let's try this again. There we go. And hopefully, yeah, we now have much more space in here to work with. Perfect. So that was the first part. Let's now try to paste in the last part. Okay, well, that looks good. Everything's looking good. Alright, so now that we have our modules copy-pasted here, now it's time to connect them. So I'm gonna have to connect the outputs from this one in here, and the second input number also needs to go in between here into these lamps right here. And then I'm gonna have to connect these outputs from the divider into the binary to BCD. And then I also need to add in some comparator logic like I did over here to block the signal from going in when we're not dividing. So yeah, I'm just gonna quickly do that off camera, connect everything. Well, I say quickly. This is gonna take me at least 2 hours, but after that we should have a fully working calculator that can add, subtract, multiply, and divide. Alright, everything should now be connected, and now it's time to finally give this divider a test. So I once again used a random number generator, and it gave me the numbers 28,860 and 12,541. And if everything works correctly, this should give us the answer of 2.3012. So let's do this then. Let's press division, and it's gonna start calculating. It's gonna take a while. So at the end of this video, I will do one final test where we do addition, subtraction, multiplication, and division. And I will also time it so we can kind of see, what? Am I glitching out again? So you guys have an idea of how fast or slow this is. Now, I do want to mention that since I added multiplication and division, this thing has slowed down the game a lot. So, you know, for example, when the answer pops up on screen, normally that's just maybe half a second, but it's gonna take like 2 seconds for it to fully show up. But I guess that's not surprising since I'm loading this entire calculator. That's like an extra 200 to 300 chunks it needs to load. Okay, the answer is 2.3012, which is correct. Well, almost. There's actually a 5 over there. So the real answer is actually 2.3013. But again, this calculator doesn't round up numbers because it literally only works with 4 digits after the decimal point. But again, this is close enough for me. I'm just really happy that this works. But that doesn't mean we're done. There are still 4 more things I want to do in this video. First of all, I want to build a random number generator for this calculator because to get these numbers, I've been looking at my laptop or my phone to randomly generate a number between 1 and 35,535, which is not ideal, because the point of this calculator is that you can do it entirely in Minecraft. Because what's the point if I make this entire thing in Minecraft if you still need to grab another device if you can't decide on the numbers? And after that, I want to do a full test of everything this calculator can do. Then I also want to update this map. So right now it doesn't have the division module right here yet. We still need to update this little part right here. And after everything is done, after this entire calculator is complete, I want to check how many hours this took me to build. In case you didn't know, you can use a /time command to display the amount of ticks that have passed in a world. And if you then divide that number that it gives you by 72,000, you will get the amount of hours played in that world. And the reason it's 72,000 is because it counts the amount of game ticks, and 1 second has 20 game ticks. So 1 hour has 72,000 ticks. So I'm gonna get to work. I'm gonna be building a random number generator for this calculator. I don't think I'm gonna show too much of the building process because I'm gonna be honest, this project is starting to burn me out. I have spent so many hours on this calculator and on these videos. But yeah, these videos take a huge amount of time, not only to build the calculator and record, but also editing. These videos take almost 8 hours to edit. And editing is not something I enjoy. So yeah, I'm just gonna get to work and build that random number generator. Well, that took more work than I expected. So yeah, this thing over here right above my binary to BCD, this is a random number generator. Ow, I just bit my tongue. Oh, that hurts. So like I said, I'm using 50/50 randomizers for every bit. So there are 16 bits, so there are 16 50/50 randomizers. So you can see in this dropper we have a snowball and a diamond sword. The diamond sword will give us a signal strength of 3, which means this repeater is going to be turned on, but the snowball is only going to give us a signal strength of 1. And then what this thing does over here, this is just another smaller binary to BCD converter, because now that we have generated a 16-bit binary number, now we need to turn that into BCD, because if you remember, our display over here works by inputting every number digit by digit. So if you have, for example, 32, you're not inputting 32, you're inputting a 3, then you wait a bit for it to show up and process it, and then you put in a 2. So that's what the binary to BCD converter does. It takes the binary number and then it converts it into separate signals for every digit. And it's basically the same concept as our binary to BCD converter over here. This one is for the answer to show up on our display. But you might be able to spot a slight size difference here. That's because if we multiply, well, our answer is going to be 32 bits. So this is a 32-bit binary to BCD. This right here is just 16 bits. And the difference in size is insane. Why is the 32 bits so much bigger? So there was one last problem I had to face, which is that by inputting these numbers, there's a delay in between the signals, because, you know, this thing needs time to process it. And that's what these repeaters do. They create that delay. So this entire thing should be synchronized. So the answers, the BCD signals will come out over here at the exact same time. And then we have these repeaters here to create that delay in between the digits. So they both need to go into these lines for going into the display, and they also need to go into our BCD to binary converters to actually make the signal that we can use to calculate stuff with. So I guess it's now time to test this. So I've put a random number generator button over here in between the numpad and the lever that controls which number you're inputting. So right now input number 1 is selected, meaning that if we press this button, it will generate the first input number. So let's press this button and see it in action. Oh, I think I can see the signal. It should pop up on screen any moment now. All right, that is our first digit. And a bit of time later, it should generate the second digit. And the third digit is also on screen right now. And I think there's going to be one last digit. There we go. That's our number, 26,862. Let's now generate the second input number. I'm not going to cut anything in the video. It's going to be uncut footage, but I might speed it up. So here we go. And there we go, that's our number, 10,299. So that's the random number generator. Pretty cool, I'm really happy with it. Now let's do the other things we said we would. And we're gonna start with updating this map. So I'm gonna take these, and I think this one as well. You know what, I'm just gonna update all of the maps. Okay, the game was struggling a lot with updating these maps, but now you can see the multiplier over here when we're dividing. We multiply the first input number by 10,000. That's what this array of adders is for. And then it leads into the division unit, which looks like an absolute mess on a map. It's kind of beautiful though. I really like this. And then up here, of course, we have the random number generator, so you can kind of follow the lines here. So the redstone line that's responsible for the random number generator is over here, I think. So it goes over like this, then it goes like this over here, and then it goes up, all the way up over here around like this, and then it travels up. That's what these gray blocks are for. These are the slabs. And then it goes over here. Oh my goodness, it's so hard to control it. And then it leads into this line of droppers. Next it goes through this binary to BCD. And then yeah, we got the redstone lines over here joining up with all of these lines going into the display. This map looks so cool. I absolutely love this. So now let's give this calculator one final grand test, and after that we will call this project finished, and then we'll take a look at how many hours this took me. So I'm going to be using these two numbers we just generated for the first operation, which is addition. Let's see if it gives us the correct result. Okay, I think something is wrong. It's been a full minute and nothing is happening. Oh, of course. So yeah, in case you guys haven't seen this, I have some command blocks over here. These are not here to make the calculator work. This is just to add and remove the ticking areas, because with ticking areas it takes like 5 seconds for a block to... Yeah, see that? That's how laggy it is. And I don't think the ticking areas are up right now. Oh, I can't even press this button. Yeah. So yeah, I'm using these command blocks to add and remove the ticking areas whenever I need to. And I actually turned them off so the signal couldn't go into the adder and into the system. So Of course we're not getting any results. And stop the timer. That is only 30 seconds. This was definitely faster at some point. I think it's now twice as slow. Like I said, the game has slowed down a lot. And now I'm gonna be using the random number generator once again to randomly generate me 2 more numbers that I can use to subtract. Alright, this time it gave me 2 really big numbers, and this should give us a negative result. So let's press the subtraction button and let's see how long this takes. There shouldn't actually be too much of a difference because I think it's only 1 extra CCA it uses. Oh, I actually forgot to start my timer there, but I'll put the number up on screen. And I just checked and this answer is correct as well. I mean, it's not like I'm expecting something to go wrong. I mean, if it does give a wrong answer, it's probably just a piece of redstone dust that I forgot to place or something. So yeah, I'm gonna reset this and I'm once again gonna randomly generate 2 more numbers for us to multiply. Alright, let's multiply 5,372 with 51,331. And I'm gonna start the timer right now. And stop it. That only took about 35 to 40 seconds. Not very big of a difference to the addition and subtraction modules. So 5,372 times 51,331 is indeed 275,750,132. Now let's do division. Alright, the calculator is ready. Let's divide 10,460 by 48,262. This one is gonna take a lot longer than the other ones though. Okay, there it is. So that was almost 3 minutes. That's a long time. But we did get a correct answer. And I'm really happy about that because I actually had to do some modifications to the division module. There were still a few things wrong with the logic to get the clock started at the correct position, but now it seems to be working perfectly. Ladies and gentlemen, I'm glitching out again, but we have a working calculator. This project has been absolutely insane. Like I said in the first video of me starting to build this entire thing, I wouldn't say I'm a noob in redstone, but I'm definitely new to making calculators. This has been a fun little challenge for me and I'm really happy I made it through to the end. And again, it's all thanks to Noobby and MadBadWings. These 2 guys really helped me a lot. Now before I say goodbye to this calculator and call this project finished for once and for all, let's first check how many hours this took me to build. So I'm going to be using this command and it will show me the amount of game ticks that have passed in this world. And again, if we divide that by 72,000, we will get the amount of hours I have been playing in this world. Now unfortunately this number is actually too big, so we can't divide this by 72,000 with our own calculator. That would have been amazing. Okay, wow, so 9,164,231 game ticks divided by 72,000 equals 127 hours. That is an insane amount of time. I spent over 125 hours building a calculator. That's absolutely insane, and that's not even counting the amount of hours I spent editing and also writing the scripts for these videos. I think in total it's close to 150 hours of work. But I'm so happy I did it because I learned so much and I have this amazing calculator. I absolutely love this build. But yeah, after over a month of work in this world, I'm finally gonna leave it behind because that's all I wanted to do. I have achieved everything I wanted to achieve. So about 6 weeks ago I uploaded a cinematic showcase of this calculator. If you haven't seen it, I highly recommend watching it because It's epic and I'm really proud of it. And for the people that watch these videos to learn something more about how to build a calculator and how binary works and how you can translate that into Minecraft, I really hope you learned something, and I really hope you enjoyed all of these videos because I spent a lot of time on this. So anyways, that was it for me today. I really hope you enjoyed, and I'll see you hopefully in the next video. Goodbye.